Hello everyone, I am Mrs. D. Shanti Chillaya, working as Assistant Professor in EC Department. I am going to take the topic Open Loop and Closed Loop Configuration in Linear Integrated Circuits. Op-amp configurations are defined by whether feedback is used to control the output. So it is here, the configuration is classified as open loop and closed loop configuration in an operational amplifier. Before going into what is open loop and closed loop, we should know what is op-amp. Op-amp is an operational amplifier with two input terminals and one output terminal. The symbol is shown here. Two input terminals are designated as inverting and non-inverting terminal, and one output terminal, it is given as output terminal. It requires external power supply plus or minus VCC. Generally, it ranges from plus 15 volt to minus 15 volt. Generally, open loop has no feedback and it allows maximum gain. It causes saturation, making it ideal only for applications such as comparators. Whereas closed loop, it is negative feedback and it feeds the output back to the input, reducing the gain for stable linear operation in amplifiers. General applications are voltage followers and filters. What is open loop configuration? No feedback is applied from output to input. It is shown in the figure. Two input voltages are given at the two terminals V1 and V2 and output voltage is obtained. Op-amp operates with very high open loop gain. The output easily saturates even for a very small input voltage. Very small differential input voltage Vin is equal to V plus minus V minus drives the output to positive or negative saturation, which is plus Vsat or minus Vsat. The applications are generally, it is used as comparator, zero crossing detector or in nonlinear circuit. The major disadvantage of open loop configuration is it cannot act as a linear amplifier because it is easily driven into saturation. The open loop gain is given as AOL. It is typically very high in the order of 10 power 5 to 10 power 6. A small differential input voltage produces very large output voltage approximates to plus Vsat or minus Vsat depending on the magnitude of the difference in voltage. It is practically unusable for linear amplification. The main applications are it is comparator used as zero crossing detector and window detector. Now we will discuss the features of closed loop configuration. Closed loop configuration is nothing but a portion of the output signal is fed back to the input terminal, usually via a resistor RF. It is feedback resistor. The feedback type can be either positive or negative feedback, and primarily it is negative feedback, and the gain is controlled and stabilized. It is used to achieve stability and control. The gain is reduced and it is designated as closed loop gain ACL, and it is dependent on external components, resistors or capacitors, and not the amplifier's internal characteristics. The closed loop configuration, majorly it is classified as inverting amplifier, non-inverting amplifier and voltage follower. We will discuss the circuit of inverting amplifier. In an inverting operational amplifier configuration, the input signal is applied to the inverting terminal through the input resistor R1, while the non-inverting terminal is typically connected to ground. It is shown in the figure. The setup uses negative feedback to produce an output signal that is 180-degree out of phase with the input signal. If it is an input is a sinusoidal waveform, the output is 180-degree out of phase with the input signal. The feedback resistor connects the output to the inverting terminal. The voltage gain is given as minus Rf by Rin. It is calculated by considering the ideal characteristics of the op-amp. The ideal characteristics is current entering into the input terminal is 0 and the difference between the voltage between the input terminals inverting and non-inverting is considered to be 0. Hence, the output voltage V0 is given as V input into Rf by R1. Hence, V0 by D, which is the voltage gain AV, is given as minus Rf by Rin. So, negative indicates the output voltage is 180-degree out of phase with the input signal. In this circuit, the virtual ground concept comes into effect because the non-inverting terminal is grounded and the op-amp acts to keep the differential input voltage at 0. The inverting terminal is held at 0 volt, creating a virtual ground. Thus, the voltage is calculated V out by V in is equal to Rf by Rin. The input impedance is approximately equal to the value of the input resistor Rin because the signal seeing up to virtual ground through that resistor. Output impedance is ideally 0, though in practice it is very low due to negative feedback. Now we will discuss the feature of non-inverting op-amp. In the non-inverting operational amplifier configuration, the input signal is supplied directly to the non-inverting input terminal. This produces an output that is in phase with the input signal. It is meant that there is no phase shift or 0 degree between the input and output. The feedback is applied to the inverting terminal through resistor Rf and the input resistance R1 is also connected to the inverting terminal. So the voltage gain is given as AV is equal to 1 plus Rf by R1. The closed loop gain is always positive and it is greater than or equal to 1 as it is given in the equation. It has high input impedance because the signal goes directly into the non-inverting terminal. The input impedance is extremely high, often approaching infinity in ideal cases, which prevents the amplifier from loading the signal source. It has a low output impedance. Like most op-amp circuit, it offers very low output impedance, allowing it to drive various loads effectively. The negative feedback is portion of the output voltage is fed back to the inverting terminal via voltage divider Rf and R1 are input to stabilize the gain. The major applications of non-inverting amplifier are voltage follower, which is otherwise called as unity gain buffer, in which V0 is equal to Vin, providing an isolation from high to low impedance. It is also applied in audio preamplifiers to maintain single phase integrity, and it is also used in active filters, mainly low pass or high pass filters. Now we will discuss the application of non-inverting amplifier, which is the voltage follower. It is a special case of non-inverting amplifier with unity gain AV is equal to 1, where the output voltage directly follows the input voltage. Hence, it is V0 is equal to Vin. The circuit is shown as given in the slide, that is output is fed back directly to the input. It acts as a buffer or isolation amplifier, providing high input impedance and low output impedance, which prevents loading effects between high impedance sources and low impedance load. The main applications are impedance matching circuit, buffer circuit, isolation between stages. The circuit diagram is connected directly back to the inverting input, creating 100% negative an voltage amplification of attenuation. It has high input impedance and low output impedance. It is used to isolate high impedance signal source, for example, a piezoelectric sensor or pH probe from low impedance load, which is an AC input, to prevent signal distortion. It also protects sensitive, weak signal sources from being loaded down, and frequently used in circuit design to maintain signal integrity. Thus, it offers major advantages in these applications. The next configuration in feedback closed loop configuration is differential amplifier. The differential amplifier is used to amplify the difference between two input signals while rejecting the common signals. It is an important building block in analog circuit design. The output is proportional to the difference between the two input voltages. Hence, the Vout is given as AD into V1 minus V2, where V1 is given to the input voltage to non-inverting terminal and V2 is the input voltage given to the inverting terminal, where AD is the differential gain. The differential amplifier uses an op-amp with two input voltages applied to inverting and non-inverting terminals through resistor network. Unlike in inverting and non-inverting amplifier configuration, here two voltage signals are given into the two input terminals to provide the difference between the output voltages. The circuit description of differential amplifier uses four resistors R1, R2, R3 and R4 to set the gain and balance of the inputs. The inverting input V1 is connected through resistor R1 into the inverting terminal of the op-amp, and V2 is connected through resistor R2 into the non-inverting terminal. The feedback resistors R3 and RF connects the output back to the input. The grounded resistor is R4 to form a voltage divider. If V1 is equal to V2, output should be ideally 0. If V1 is not equal to V2, output is proportional to the voltage difference. The differential gain is given as AD is equal to RF by Rin. The common mode signals are rejected and differential gain is nullified. The high gain is achieved with precise resistor matching. So to conclude, the comparison of open loop versus closed loop is, under open loop, the gain is extremely high, and whereas in closed loop, it is lower and it is precisely controlled. The bandwidth of open loop op-amp is very narrow, whereas in closed loop, it is significantly expanded. Stability is very poor in open loop. It can easily be saturated. Whereas in closed loop, it is high and it always applies in linear operation. In open loop, it is highly sensitive to noise and disturbances, whereas in closed loop, it is less sensitive due to self-correction. Under open loop, it is independent of output, whereas it depends on actual output in closed loop configuration. Applications of open loop are voltage comparators, whereas in the closed loop, majorly in amplifiers, filters, and oscillators. Thank you.